In this lecture, I will be reviewing the phosphoric acid, which is a weak base, and the sodium hydroxide titration. So what we did here in lab is we took 40 milliliters of phosphoric acid, which is a triprotic acid, and we put that in a beaker with a stirrer. And what we did was we titrated it with 0.1 molar NaOH. So we dropped the base on the acid. And we didn't know the concentration of the acid, which is one of the things I'm asking you to get. We know the concentration of the standard base, which is 0.10 molar. And we're trying to find, okay, what the concentration of the acid is. We're trying to find the Ka1, Ka2, and Ka3. That's it. There's 3 Kas here because we have a triprotic acid. We have an acid that can dissociate 3 protons. So therefore, it's going to have 3 separate acid dissociation constants. We're going to verify, I believe, the final pH and the initial pH. So let's get started. So we did this titration, and we added a milliliter at a time, measuring the change in pH with each milliliter. Okay, now it looks like what I have here goes from 50 to 100, so essentially I'm starting at 0 and I'm ending at 50 with the curve that I'm working with. So I'll have to work with that way. Now, so what we're watching is the pH changed with the volume of the base added. And if you've done previous titration curves with pH changes with volume, you can clearly see where the equivalence points are. So I see that my equivalence points, eyeballing it, is essentially something like this, which probably gives me something, if this is a 4, I'm looking at 4.8 maybe. So it looks like to me like the equivalence point is at 4.8. Now, why did I look at that first? Well, because 4.8 is going to give me a certain milliliter value. And I'm looking at that right here. So what is the volume at that equivalence point? And it looks to me like, if I'm looking at this carefully, this says 62, 63, 64, so it's between 63 and 64. So it's 63.5, but remember it started at 50, according to this graph, I guess. So essentially, I'm subtracting 50, and that gives me 13.5. So 13.5 milliliters is an important number because that tells me that at this volume of base added, which was 0.10 molar, I have reached the equivalence point, at least the first equivalence point. Now, what's happening here? Because it's important to know what the predominant reactions are. So at this part of the curve where we started initially, we have a certain reaction occurring. And that reaction is, and I'll write that in, let's say, a different color because I can. So let's take, we have in this part of the curve from the initial pH to the equivalence point, what we have is we have H3PO4, okay, plus the hydroxide ion. And I'm not writing this with enough space, so let's white this out too. All right, although I may have to adjust this. Let's put it lower. So let's make it lower here. Okay, so the first reaction, I'm going to go black so you can see everything. The first reaction is going to be, try to stay out of my equivalence points here. Let's throw it down here. Is going to be H, oops, not that. H3PO4 plus the hydroxide, and this is a stoichiometric relationship because the strong base will pull the H off stoichiometrically, going to drive the reaction to completion reaction, and it's going to make H2PO4 negative because you lost a proton. All right, and of course you're going to make your water. So this is the predominant reaction in this area here. Okay, and we would say at this point here, we have 100% H3PO4, and at this point right here, we have 0% H3PO4. Now, we have 0% when we start H what? H2PO4 negative. And at this point, we have 100% H2PO4 negative, right? Because as we go from this point to the equivalence point, we're driving this acid, weak acid, off. We're going to pull off one H. So this is what it takes. This is the total volume it takes from here, from 11, what was our number? From 13.5 milliliters from the 0 mark. That's how long it takes to neutralize. All right, now just from that equivalence point, the first equivalence point, I could actually solve for the concentration of the acid. Let's do that. So how do I start that? Well, I take my 13.5 milliliters of my what? Of my base, and there's something I know here. I know that at the equivalence point, the hydroxides that came from the base equal the proton that came from the H3PO4. Okay, so what I'm going to do is find the moles of NaOH, or in this case hydroxide. I divide by 1,000 milliliters to get liters. Milliliters go bye-bye, and I'm left with liters of NaOH. No big deal here, but now I want to put in the molarity, which is 0.01 moles per liter. I'm going to use the molarity equivalent here to get my moles out. And now I have moles NaOH. Now I can continue this forever, but I know that this is really NaOH or hydroxide because it's a strong base. And I know that there's one hydroxide for every one H plus. So, or in this case, if I really want to do this correctly, for every one what? For every one H3PO4. Now we're counting only the first H coming off that though. So what's going to happen here is I'm going to wind up with moles, it's hydroxide's from here. I'm going to wind up with moles of phosphoric acid. Okay? And what I'm going to do is divide by the volume. The volume of phosphoric acid that we had in the beaker was 40 milliliters, or 0.040, liters. That's the equivalent. And this would give me my concentration of my acid. Let's put that in our calculator. Okay, I can see I made my first mistake because this looks really low when I solve for it. And I see that I have a 0.1 molars, not 0.01. Okay, so let me change that and make my correction. Okay, so 0.10 molar, and this makes 0.03. So I got now 0.0338, or 0.034 molar. And that's my concentration of my phosphoric acid. Notice I didn't have to get to the final equivalence point. I can do it from the first because it took exactly this milliliters to what? Neutralize the H3PO4. Not completely, just take the one H off. So it's interesting to note you don't have to go to the final equivalence point to get that. But I got my first answer. Concentration is 0.034. Okay, so that we got there is 0.034 molar. Okay, now let's go find our first Ka. Now, if I know 13.5 milliliters is how much moles of base needed to neutralize the first acid, well, the halfway equivalence point is 13.5 divided by 2. Okay, so 13.5 divided by 2, this gives me 6.75 milliliters. So if I know what it takes to completely neutralize, to get to the halfway equivalence point, it has to be half that. So I'm looking for 56.75, somewhere around here. And that, my friends, is my max buffering position. Why do I care? I do care always because What I'm trying to find is that pH where I have equal amounts of conjugate acid and conjugate base. So I'm just guessing, eyeballing it here. If this is 1, this is 2. Looks like this is 3, and this is a 4. So it looks like I'm between 2 and 3. Let's make it 2.7. So 2.7 is my pH at the max buffering position. Well, wait a minute. pH equals the pKa plus the log of the conjugate base, which is H2PO4 negative over H3PO4, the conjugate acid. And at this position, you have half the amount of base needed, so that would make the same amount of conjugate base formed as acid left over. When you half titrate something, you're going to force what? At this point, as we did before, you're going to have 50% what? H3PO4, and you'll have 50% H2PO4 negative. That's what's happening there. And if you have equal amounts at this position, because it's halfway to what it would take to fully drive it forward, these values will be the same. And the log of whatever number over the same number, a log of 1 goes to what? 0. And then we have the pH equals the pKa. So my friends in chemistry, 2.7 equals the pKa. And to get to Ka, I do 10 to the negative 2.7.
People here.
Yeah, usually.
Examine. So where's our temper?
Look at the text. Make it not like
We have everyone
gonna go to waste.
I looked at my.
Oh no, I'm going to grade them.
When do you think they're gonna be great about?
I don't know. Today's a tough day to get them done for me today. We'll see.
Never.
Oh, never. Okay. Okay, so 10 to the negative 2.7, going from the exponent back to a number, and I get 0.001995, and that would be a concentration of, well, I'm sorry, that of course would be a Ka, okay, the Ka1, which of course is 1.9, let's make it 95, or we can go 2.0, whatever, we can keep the numbers, times 10 to the negative 3 is my Ka. Ka1. All right, that's the first Ka. All right, and of course, as we go on through this, the second Ka would be 13.5 milliliters from the, well, 13.5 milliliters from this equivalence point should give me to the second equivalence point. So let's do that. So of course 13.5 plus 13.5 gives me 27. So at 27 milliliters, now of course I had to make this difficult for myself and start at 50. So 27 plus 50 is 77, and I believe that's here. Although it looks kind of messed up, doesn't it? So I'm not sure what happened at this point. So 13.5, and this is what, 73, just making sure here. Yeah, so 77 is right here. So this is my second equivalence point. All right. And of course, in between these 2 points, of course, 13.5 divided by 2 we just found to be 6.75. So 77 plus 6.75 gives me 83.75. So 83.75, like somewhere here, is the milliliters. Okay, gets me. Oh, let's start from the first equivalence point, right? So I'm sorry. So 60. Wow. Okay, we're 60 something and a half. So 13.5 plus my 6.75. That's how I should have done this originally. 7.5 is 12, and that gives me 20.25 would be the volume I need to get, it's the value in between these two numbers. So obviously I made this difficult. Add 50 to it, so it's 70.25. 70.25 is somewhere around here. And this, of course, is my halfway between the second equivalence point. And just to roughly find that number, looks like I'm somewhere here, and of course I'm not using a straight edge. I'm somewhere right here. So 6, 7, let's make it 7.3. And this will give me my second Ka. 7.3, for the same reasons, 10 to the negative 7.3. Oops, I'm getting sloppy. 10 to the negative 7.3 is equal to what? Put that in my calculator. And we do second function 10 to the negative 7.3. It's how we go backwards from a pH. pH equals the pKa at the max buffer position. And I get 5.0, 5.01 times 10 to the negative 8. And that equals the Ka2. Now I should write the second reaction that's going on here. Okay, the second reaction that's going on, I'll put that in black. All right, is that at this point here we have 100% H2PO4. So H2PO4, okay, plus, guess what, the hydroxide is going to make H, this is by far negative, sorry, because it lost an H, HPO4 negative 2 plus the water. Okay, and we're driving that forward. So we have 100% H2PO4, and now at this point we have 0% H2PO4, but we have 100%, and you guessed it, HPO4 negative 2. We've driven it all the way from 100% at this point to 100% of that stoichiometrically. Okay? And there's my K2. Now, if you notice something, where's my K3? Where is my, shouldn't this go up and do that? Shouldn't I find the next equivalence point? Doesn't this acid have 3 protons to give? And of course it does. So why don't I see a third equivalence point? Well, it's pretty interesting. This is 11 pH, this is 12 pH, okay? And what's happening here is the reason why you don't see a nice equivalence point because, well, we are starting to approximate the basicity of the base we're using. And now why? Well, you should understand at this point, which would be 0%, 100% HPO4 negative, if you add what? If you add 13.5 milliliters from this position, so what am I saying this is? Approximately 77. So if I add 13.5 to this, that'll get my next equivalence point because, and the reason why I can keep doing that, adding that exact amount is because the amount of base I'm adding is constant. So I add 5, 10, and I get 90.5. 90.5 is right in here. And this would be my third, I added 13.5, right? Yeah. So this would be my third equivalence point. And you don't see it because what's happening at this point, we have 0% HPO4, negative 2, and theoretically, we have 100% what? PO4 negative 3. Now it's theoretical. Now I'll highlight this. Why is it theoretical? Well, PO4 is a decently strong base. It's such a pretty good strong base, it starts to do what? PO4 loves to absorb protons. So as soon as we make PO4 negative 3, it rips a what? it rips a proton away from any water that's around it to reform the acid. So it's such a strong base, we can't, it's almost as strong as the base that we're using in terms of the concentration of the weak base. Now, it's not as strong as a hydroxide, but we're using a what? A 0.1 molar solution of a strong base. All right? So because the strength of the base that we're titrating is about, or approximating the base of this conjugate base, you're just going to equal out. Or think of it, as soon as we make PO4 negative 3, it's immediately producing a hydroxide and reproducing HPO4 negative 2 as it gains an H and ionizes water. That's why you don't see, okay, another third. If the basicity of the base I was using was really, really strong, and that's pH of the base is way up here, then we could see a line. But again, we're using a dilute solution of a weak base, okay, although it still has a pretty high pH, that pH is approximating the concentration of this base here, and that's why you don't see it. But we can still use the graph. So to find the third equivalence point, I go from my, looks like 77, and add our halfway number, 6.75, and I get basically 75 and 3. We did this already, didn't we? Somewhere, yeah. No, 83.75. So 83.75 is about somewhere here, and this is my max buffering position. That pH looks somewhere in between here, so I'm going to guess 11.5. And same thing, 10 to the what? Negative 11.5 will give me my value. So back to the drawing board here. So 10 to the negative x, 10 to the negative 11.5, and this gives me a Ka, believe it or not, you can call it a K at this value, equal 3.16 times 10 to the negative 12. That's pretty weak Ka, which means the Kb is extremely strong or extremely high. And that's why you don't get that third equivalence point. So in any case, there's your 3 Ka. This is Ka 3 that we found at this point. We've got Ka2 that we found, of course, from this point. And we've got Ka1 that we found from this point. We have our 3 equivalence points. All right, boom, boom, and boom. Not sure why I need the sound effects. And we have our max buffering positions. And we have everything we need here except for the initial and final pH. So, the initial pH, how do we do that? All right, well, initial pH, we just have the concentration of 0.034, okay, sodium phosphate. And of course, my friends in chemistry, that means Na3. That really is essentially the phosphate ion. Sorry, what am I thinking about? We have 0.03, sorry, yeah, 0.034, sorry, H3PO4. Okay, so what is the pH of that? Well, it's a weak acid, so we can't take this concentration in terms of H pluses. We've got to do a what? We've got to do an equilibrium problem, okay, that we've done so many of them already. And you probably don't need to do this anymore, but if you do, here it goes. So here's a concentration initially. Here's your ice table. This is 0 and 0, minus X, plus X. Okay, so this is 0.034 minus X. That's their ice initial change in that equilibrium. And this, of course, is X plus 0, which is X and X. Now, party people, putting it equal to the Ka. The Ka of 1 is 1.995 times 10 to the negative 3. And we're going to equal X squared. And we're going to multiply that by 0.034. For those that don't know what I just did here, the K equilibrium, or Ka, is equal to the products, which is in this case these two X's, times themselves, that's where the x squared comes from, over the reactant, which is 0.034. I approximated away this x because compared to how forward this goes, this x isn't that significant. So we can approximate that away, and now I know the value of my Ka, which I plug in and I solve, and that's what I did here. And if you've done this enough, you can make this leap. And of course, we're going to take the square root of that product to get rid of that x squared. So what does x equal here? Okay, x equals 0.00824 in my case. What did I just solve for? I solved for the concentration of the H+. So we'll do a negative log to put that into a base 10 exponent. So negative log of my second answer gives me a 2.08 initial pH. And let's see what we got here. Yeah, 2.08, and I'm about at 2. So that kind of confirms it. And then the final pH. Well, at the final pH, after I've neutralized all my acid, okay, I'm left with just the extra base. All right, so at this point, this is the final titration point. So what number is that? Oops, sorry. What is that number here where I have that equivalence point? I said 90.5. So 90.5 is where the last equivalence point is. This is where I've supposedly, theoretically annihilated all of my what? H2PO4, and I should write it there as my third equation, right? I forgot to do that, bad Grodsky. So the third equation, which is happening right here, is the HPO4 negative plus the hydroxide makes what? It's -2, sorry. PO4 -3 plus the water. Now the problem is that this immediately reacts with the water to reform this. That's why it levels out. Okay. So in any case, that's the third predominant reaction in that part. But what I'm getting at here is the final pH is just because theoretically you've driven off all of the acid into this. Okay. So any extra what? Base you add beyond this point is responsible for the pH. All right, so watch what we do here. We have 92.5, I believe, or 90.5 is my equivalence point. Subtract that, well, I'm saying 92.5. Subtract that from 100. Okay, so I basically got, how many milliliters did I add? 9.5. So from all of this, I've got 9.5 milliliters of OH I've added. Divide by 1,000 to get a liter. I know the molarity of my base is 0.10 moles for every 1 liter. So now I got moles. To find the concentration, I divide it by the total liters. So how many liters did I add in this case? So remember, I started at 0 and it's 50. So this is actually 40. If it's 9.5 milliliters minus 40, so we've got what? 40.5. So hold on, let me just do this correctly. So we added, so to get to this point, we added a total of, the total volume is going to be at this point 50 plus whatever is in the beaker, which was 40 milliliters. So I've got 90 milliliters, which is 0.090. Okay, I found the moles of hydroxide. We've added past the what? At this point, the pH is based on how much base you've added to this diluted solution. It's theoretically has been neutralized by the strong base. Still find that number, and we're done. 9.5 divided by 1,000 times 0.1, and divide that by 0.09, and I get a value which should be equal to moles over the molarity to be 0.0106. That's the molarity of the hydroxide in this solution. We want the pH. So what do? I do negative log to get my pOH. So I hit negative log of my answer, And I get 1.98 is my pOH. Okay, subtract that from 14, because the pH plus the pOH equals 14. So we do that, and we get a pH to equal, the pH final is 12.0, I round to. And that's essentially where I was getting at, right? 12.0. So I have the final pH, I have the initial pH, which I needed the Kas for. I did not need any equilibrium problem for the final pH because I was dealing with just the strong base and this much beyond the stoichiometric endpoint. All right, the Kas I have, and I've marked my equivalence points. We are finished. I hope that helped.